Most deep learning resources fail at the same point. They teach the idea, but not the practice. D2L Zh solves that by being more than a textbook. It is a Chinese edition of Dive into Deep Learning, an open, free, runnable deep learning textbook that brings concepts, math, code, and engineering practice together in one place. Think of it like a cookbook that gives you the recipe, the ingredients, the tools, the cooking demo, and a place to ask what went wrong when the dish fails. That matters because deep learning is not something you really learn by reading alone. You learn it by running, changing, and breaking things, then seeing what happens. The bigger idea here is not just a textbook with code. It is a learning system that can be edited, run, discussed, and improved by the community. In a field that changes fast, that is a huge advantage. Static notes age quickly. Reproducible examples do not. If you treat this like a passive, read-only book, you miss the real value. Run the notebooks, change the code, and turn each lesson into an experiment. But there is a catch most people miss.
Before you dive in, there is one thing that makes this resource click. It is not a book you read once, it is a lab you run. If you treat it like a passive textbook, you will miss the whole point. The fastest way to learn here is to execute the notebooks, change the numbers, and watch the results move. That turns abstract ideas into experiments you can feel. To get there, you should already be comfortable with Python, which is the main programming language used here, and Jupyter Notebook, which is an interactive page where code and notes live together. NumPy helps with fast array math, and basic linear algebra means things like vectors and matrices, which are the data shapes deep learning uses all the time. Basic calculus matters too, because it explains how models learn by following slopes. You also need machine learning fundamentals, a deep learning framework such as PyTorch or MXNet, which is the library that actually builds and trains neural networks, and Git and GitHub for tracking code and syncing work. If any of that feels shaky, review it first. But do not just study it on paper. The real gain comes when you pair each idea with code you can run. And once your setup is solid, the next thing that matters is version consistency, because small differences there can change everything.
The fastest way to make this click is not to start with theory. It is to run a tiny chapter example and see the math become code in your own environment. That is the core idea behind D2L, or Dive into Deep Learning, which is a book built around executable notebooks, meaning code you can run right away. When you do that, you are not just reading about tensors, which are multidimensional arrays of numbers. You are proving that your setup works, and you are connecting the equation to the result in the same minute. Start small, create a tensor, apply a simple transformation, and inspect the output. That tiny loop beats passive reading because it gives you a baseline you can trust before you move on to bigger models. If you skip this and treat the chapter like a textbook, you can waste hours later chasing a version mismatch or a hidden setup issue. A lot of teams avoid that by verifying the notebook first, then comparing it with their installed framework version. Source, https://github.com/d2lai/d2lzh. Here is the simplest pattern. You import PyTorch, which is a deep learning library, then make a tensor called x with 3 values. After that, you compute y as 2 times x plus 1. That line is doing something useful. It shows how a mathematical expression maps directly to runnable code. When you print both, you should see x as 1, 2, 3, and y as 3, 5, 7. The point is not the formula itself. The point is that you can modify it and immediately see what changes. That is far better than memorizing equations in isolation, because you learn how the framework actually behaves. A common mistake is to read the notebook without touching it. Do not do that. Change the numbers, rerun the cell, and keep a local copy of your edits so you can track experiments cleanly. If the output differs from the book, use the forum to compare notes before you assume the code is wrong. But there is a catch most people miss. Most people think the hard part is learning the formula. It is not. The hard part is turning that formula into code that actually behaves the way you expect. That is the gap D2L wants you to close here, not just reading an equation, but seeing how it becomes a working model. A model is just a rule that maps inputs to outputs. In this tiny example, the rule is a line y equals w times x plus b, which means multiply by a slope, then add an offset. The code starts with synthetic data, which means fake data made for testing. Here, y is defined as 3x plus 2, so the line is perfectly known. That is useful because it removes noise from the lesson. Then the code guesses w as 3 and b as 2, runs the prediction, and checks whether the result matches the target. That simple check matters in production, because tiny implementation mismatches are a major source of silent bugs. A paper can look right while the code is wrong. The safest habit is to pair each equation with a runnable example, not treat the notebook like a read-only textbook. But there is a catch most people miss. The real power of D2L is not that you read the code. It is that you change it. That sounds simple, but it is the difference between memorizing and actually understanding. Here, a hyperparameter is just a knob you can turn, like a learning rate or a weight value, to see how the model behaves. In this tiny example, x is a list of numbers from -1 to 1 and w is the knob. When w changes from 1, 0 to 2, 0 to 4, 0, the output stretches in a predictable way. That is the point. You are not guessing anymore. You are watching the math respond in real time. This is why the notebook is not a passive textbook. If you only read it, you miss the most useful part, the feedback loop. Run the cell, change one value, run it again, and compare. That beats the naive approach of staring at equations and hoping they stick. In real projects, this is how teams debug and improve systems. They test one change at a time so they can see what actually moved the result. A common mistake is to treat the notebook like a read-only page. Don't. Save a local copy of anything you modify so you can track what changed, especially when you start testing data, parameters, or model structure. If your output looks different from the book, check your environment and compare versions before assuming the code is wrong. And if an edge case still feels unclear, the forum is a good place to compare notes with other readers. But once you start experimenting, a more interesting question appears. The real power of D2L is that it is not just a book. It is a teaching system. It blends explanation, math, runnable code, and discussion in one place. That matters because people do not learn at the same speed. Some readers need the idea first. Others need to see the equation. Others only trust it after they run the code themselves. A good workflow is simple. Read one section. Run the notebook. Then ask questions in the forum when something feels off. That mirrors how strong engineering teams learn and practice. Read, test, discuss, refine. It also solves a production problem that shows up in onboarding and education. When 10 people get stuck on the same detail, a forum and runnable examples remove the bottleneck instead of making one expert answer the same question 10 times. Here is a tiny example of that learning by doing loop. This code makes a tensor, which is just a labeled block of numbers, then computes the mean, which is the average, and the standard deviation, which measures spread. Running it lets you check the idea against reality. That beats passive reading every time. Source, https://github.com/D2LAI/D2LZH. A common mistake is to treat the book like a read-only textbook. Don't do that. Modify the code, compare your output, and keep a local copy so you can track what changed. But there is a catch most people miss. The last step is the one that keeps everything useful after the first read. Treat the repository like a living reference, not a frozen book. That matters because deep learning changes fast. Frameworks update. Best practices shift. A notebook that worked last year can break today if an API changed or a default moved. In production, that is not a small annoyance. It can mean broken code, mismatched behavior, and hours lost to debugging a problem that was never really in your model. D2L's open, community-driven format makes it easier to keep up as the field moves. Source, https://github.com/D2LAI/D2LZH. A practical habit is to check your environment before trusting any example. That is why this tiny code block matters. It prints the PyTorch version, which is the framework release you are actually running, and it checks whether CUDA is available, which tells you if your code can use the GPU, the graphics processor that speeds up training. If the notebook assumes one version and your machine has another, you want to know that immediately. Source, https://github.com/D2LAI/D2LZH. So do not just read the code. Run it. Modify it. Compare editions, verify your installed library version, and keep your examples aligned with current APIs. A common mistake is treating the repo like a passive textbook. That feels safe, but it hides the real lesson. The moment you experiment, you start noticing where the docs, the notebook, and your environment disagree. Keep a local copy of the notebooks you change, and use the forum when a result looks different from the expected output. But there is a catch most people miss.
Most tutorials stop at the idea, and that is exactly where people get stuck. D2L Zh is built to close that gap. Think of it like a cookbook that does not just show the recipe. It gives you the ingredients, the tools, the cooking demo, and a place to ask why your dish failed. The text explains the concept in plain language. The math turns that idea into something precise. The code makes it executable so you can run it. And the discussion forum fills in the blanks when your results do not match the page. That matters because deep learning changes fast. A static note ages quickly, but a living learning system can keep up. Source, https://github.com/D2LAI/D2LZH. The big idea is not just a textbook with code. It is a continuously editable system for learning, running, discussing, and improving the same material. That is why it works so well for a university ML course or an engineering onboarding program. A learner can read one chapter, open the notebook in Jupyter, which is an interactive coding notebook, and try the example right away. If something looks off, they can ask in the forum and compare answers with other readers. That is much better than passively reading equations and hoping they make sense later. One common mistake is treating it like a read-only textbook. Do not do that. Run the notebooks, change the code, and turn each example into a small experiment. Keep a local copy too, so you can track what changed when you tweak data, hyperparameters, or model structure. But there is a catch most people miss.
So the big takeaway is that D2L Zh turns learning into a layered pipeline: idea, math, code, and community all working together. Quick question: what should you start with when you want to understand a chapter? Start with a runnable example, because seeing it execute makes the rest easier to follow. Quick question: why treat the repo like a living reference? Because the notebook, book, and forum together help you inspect, modify, and fill in the gaps as you learn. D2L Zh is most useful when you treat it as a working lab, not a book you just skim once. The real power is in the loop. Read one chapter, run the notebook in Jupyter, ask questions in the discussion forum, then change the code and see what happens. That matters because deep learning sticks when you connect the math to a live example. If a university ML course or an engineering team onboarding program uses it well, learners can move from a simple chapter on regression or image classification to a small internal project much faster than they could from slides alone. The common mistake is to read it passively and think understanding will come later. It usually does not. Run the notebook, break it on purpose, fix it, and learn why the result changed. Also verify your environment and compare the additions code with your installed framework version, because library differences can waste a lot of time. The best next step is simple.